Okay, welcome back if you've had a little break. In this section we're going to look at the neutralisation reactions of carboxylic acids, and then we're going to go on and look at the oxidation of alcohols. So beginning with neutralisation of carboxylic acids. Carboxylic acids can be neutralised with bases, just like any other acid can. So bases are substances which can neutralise acids, and bases are metal oxides, metal hydroxides and metal carbonates. So if you see the name of a substance and it's the name of a compound, the first part of the compound is a metal and then it ends in oxide, hydroxide or carbonate, you should recognise that as a base. So the base reacts with the carboxylic acids to produce water and an alkanoate salt. So you've got carboxylic acids, so you've got different products depending on the type of base, basically. All of the different reactions will always produce water and this salt, alkanoate, which we'll look at in a little bit more detail in a minute. But when we've got a metal carbonate, it produces salt, water and carbon dioxide. So hopefully that's easy enough to remember. Carbonate also gives you carbon dioxide. So when we're naming these alkanoate salts, the name of the salt has two parts. The first part is the name of the metal in the base, and the second part is the name of the carboxylic acid with the ending changed to O8. So that's why I'm calling them alkanoate salts. It's probably easiest to understand this by looking at an example. So if we look at the neutralisation of ethanoic acid with this base here, pause the video or think about what this base might be called. Okay, well this base here is called sodium hydroxide. So you've got the sodium here and then you've got the hydroxide ion here. And that's reacting with ethanoic acid and then it's producing this salt here. So the first part of the name of the salt is coming from the metal in the base. So the salt is called sodium because it's sodium hydroxide, and it's called sodium ethanoate because it's ethanoic acid. So the ethanoate is coming from the ethanoic acid, but with the oic acid changed to O8. So ethanoic acid plus sodium hydroxide makes sodium ethanoate plus water. What's happening here is, if you can remember, thinking back to the previous page, these alkanoic acids can ionize, meaning that they can lose this hydrogen atom, so in the form of an H plus ion. So the hydrogen ion, H plus ion, is going to combine with the hydroxide ion in the base here, and that's going to give you water. So that's where the water is coming from, and what you're then left with is a sodium ion and an ethanoate ion. But we would call it, if we were to evaporate off the water, we would be left with the salt, sodium ethanoate. Okay, two more examples here then. Propanoic acid plus magnesium carbonate, that's going to give us a salt called magnesium propanoate. So this is the salt, plus water plus carbon dioxide because it was a carbonate here. So again, magnesium is coming from the name of the metal in the base, and propanoate is coming from the name of propanoic acid. And then in example 3, heptanoic acid plus calcium oxide would make calcium heptanoate, that's the salt there, and water. I'm just going to add into the notes something just to maybe illustrate this reaction a little bit more clearly using the molecular formula, or a kind of version of the molecular formula for heptanoic acid. So hept, how many carbon atoms is it going to have? Well, it's going to have, hept means 7, it's going to have 7 carbon atoms altogether. In my little version of the shortened structural formula, I'm going to say C6H13, because remember the general formula is CnH2n plus 1 COOH. So I'm going to write this out. For heptanoic acid, it would be C6H13COOH to give us the 7 carbons altogether, plus calcium oxide. So see if you can get the formula for calcium oxide on your own by pausing the video. Okay, so what you should have remembered is calcium has a valency of 2, or it would be 2 plus. Oxygen has a valency of 2, so it would be 2 minus, meaning we just need 1 of each of these ions. So calcium oxide, I'm not going to write the ionic formula, I'm just going to write the ordinary formula, CaO. and I'm then going to make calcium heptanoate. So this one is going to be slightly different because our alkanoic acid ion would only have a minus charge. So what we're going to end up with is actually 2 of these heptanoic acid ions for every 1 calcium ion. So I'll show you what I mean by that, and I'm just going to have to change that here. So C6H13COO minus, and I'm actually going to need 2 of these for every calcium ion, like I say, because each calcium is going to be 2 plus. So I'm going to need 2 of these. So I would put my 2 outside the brackets here, plus H2O. Now, if I wanted to then balance that equation, what I would need to do would be to say, I would need 2 of these. Okay, so it might be worth adding that in. You probably wouldn't be asked about the details of this reaction, to be honest, but again, it's just kind of background knowledge that's worth knowing. Okay, so we're now going to look at another 2 examples of neutralisation of carboxylic acids. And in question 6, it asks you to write word and short and structural formula equations for the reaction of methanoic acid, first with magnesium oxide and secondly with calcium carbonate. So I would like you to pause the video now and attempt those questions yourself before you look at my answers. Make sure you pause the video now. Okay, so you'll see the answers here. So A, methanoic acid plus magnesium oxide makes magnesium methanoate plus water. So we've got the short and structural formula of methanoic acid written as we would write it, as we'd written it on the previous page, plus magnesium oxide, and then we're making magnesium methanoate. Now, remember, just like in the example of heptanoic acid, which I just talked about, each methanoate ion, we'd call this the methanoate ion. Each methanoate ion has a charge of 1 minus, whereas magnesium, because it's in group 2 and needs to lose 2 electrons, will have a charge of 2 plus. So we need 2 methanoate ions for every magnesium. And then we're making water in that reaction as well. And then just to balance the equation, if we want, we can add a 2 in front of our methanoic acid here. Similarly for B, we've got methanoic acid plus calcium carbonate, and that's going to make calcium methanoate this time because calcium is the metal in the base, plus water plus carbon dioxide because it's a carbonate. Just notice how in these equations, I've not been able to fit all of my products onto one line, but I've still kept them on the right hand side of the arrow. We would always do that rather than writing the products underneath the reactants. And then again, if we look at the short and structural formulas, we've got our methanoic acid plus calcium carbonate. Again, I hope you can work out the formula for calcium carbonate based on the charges. So calcium would be 2 plus, carbonate is in the data book, it's CO3 2 minus, so there would be one of each in the formula. And then when we look at calcium methanoate, because calcium is calcium 2 plus, we would need 2 of the negatively charged methanoate ions for every 1 calcium ion, and we're making water, and I've forgotten my carbon dioxide in this equation here. And then again, just to balance it out, we'll put our 2 in front of our methanoic acid. So I did say you won't really be asked about this type of equation, but it is worth remembering this is going to come into play when we look at the structure of soaps later on in the topic. Okay, so I know I'm rushing through things fairly quickly, but we are trying to cover quite a lot of ground with this topic, and we'll then review a lot of it when we look over the next 2 topics on cosmetic chemistry and chemistry of cooking. So I'm going to move on now. And we're going to look at the oxidation of alcohols. So we've had a quick rattle through of alkanes, alkenes, alcohols and carboxylic acids, and we're now going to move on to something that's completely new to hire, which is oxidation of alcohols. Again, I'm going to read through the notes and I'm going to try and explain things in a little bit more detail where I can. In this section there'll also be a link to an experiment which you need to watch. So, oxidation of alcohols. Oxidation is loss, that's what you've learned so far. We've learned oil rig, and we should remember that that refers to electrons. So oxidation is loss of electrons. But we can think of it slightly differently when it comes to carbon compounds. So oxidation of carbon compounds involves loss of electrons or an increase in the oxygen to hydrogen ratio. So this is what the SQA talk about, an increase in the oxygen to hydrogen ratio. An easier way of thinking about it is that this means that there will be more oxygen relative to hydrogen. So oxygen must be added or hydrogen removed. So what I like to think of it is oxidation. The way I like to think of it is oxidation. That kind of intuitively you think of that as adding oxygen, right? Oxidation means adding oxygen. But if we're adding oxygen in terms of carbon chemistry, the other thing we can do for oxidation is removing hydrogen. So oxidation is adding oxygen or removing hydrogen. You can change oil if you want to oxidation is loss of hydrogen, but that might be confusing. So oxidation is an increase in oxygen or a decrease in hydrogen. Conversely, reduction of carbon compounds, so we've learned reduction is gain of electrons, but in carbon chemistry we think of it as a decrease in the O to H ratio. This means that there will be less oxygen compared to hydrogen, so oxygen must be removed or hydrogen added. So if you can remember that oxidation means adding oxygen, then that's the key thing, and you can then work from there. So if oxidation is adding oxygen, reduction must mean taking oxygen away. And then if you just can remember that you do the opposite thing to hydrogen, so reduction means taking oxygen away or adding hydrogen in the context of carbon chemistry. We'll do plenty of practice of this over the next few pages. Okay, so first of all, it's worth doing a little bit of practice of calculating the O to H ratio, the oxygen to hydrogen ratio. This should be nice and easy. It's just a case of counting up the number of each type of atom in the formula. So for example, ethanol has this molecular formula here, CH3CH2OH. The O to H ratio is 1 to 6 because there is 1 oxygen and then there are 1, 2, 3, 4, 5, 6 hydrogens. So O to H ratio is just 1 to 6. What I'd like you to do is pause the video now and try question 1. Okay, so here are your answers here. So methanoic acid has the formula HCOOH, if you look at the shortened structure. When I'm doing these, I prefer to write out O to H, because that's what we're looking at, the O to H ratio, and then I know to write down the number of oxygens under the O, so there's 2 oxygens, and the number of hydrogens under the H, 2, so it's a 2 to 2 ratio, which I've then simplified to a 1 to 1 ratio. And then similarly with propanol, I find it easier to write out O to H first, and then I just count the number of oxygens, 1, and count the number of hydrogens, 1, 2, 3, 4, 5, 6, 7, 8. So it's a 1 to 8 ratio in propanol. So what you can see from this is we would say that methanoic acid has a higher O to H ratio, meaning that there is more oxygen relative to hydrogen. Propanol has quite a low O to H ratio, because if you can see that there's 8 hydrogens for every 1 oxygen, so there's quite a low ratio of oxygen to hydrogen. So it might be worth adding this in. So you would say methanoic acid has a high O to H ratio. Okay. So you could say that methanoic acid is a more highly oxidized form of a carbon compound compared to propanol, if you wanted to. Right. So moving on now to oxidation, to put what we've just learned in a little bit more context. First thing to look at is combustion. So ethanol burns cleanly in oxygen to produce carbon dioxide and water. And because in this reaction we're adding oxygen, combustion is a type of oxidation reaction. So we could say that ethanol is oxidized in this reaction as oxygen is added. So question 2 says, write a word equation and a balanced symbol equation for the complete combustion of ethanol. Pause the video now and have a go at that question. Okay, so I've written out 2 different versions. For some reason, I started off doing the shortened structural formula of ethanol, then I decided it would be better to just use the molecular formula for ethanol. Obviously, I haven't balanced this yet, so your combustion general word equation is ethanol plus oxygen makes carbon dioxide and water. That should have been nice and easy. Here's the symbol equation, and I'll just run through how I would balance this. So when I'm balancing this type of equation, I would always do carbons first, then hydrogens, and then oxygen last. So I'm going to start by looking at the number of carbons on the left-hand side. So I've got 2 carbons here. That tells me I'm going to need 2 CO2s. I've got 1, 2, 3, 4, 5 plus 1, 6 hydrogens on this side. So I'm not writing out all of my counting here. I'm just trying to speed it up a little bit. So I've got 6 hydrogens on this side. That means I'm going to need 3 waters, because 3 times 2 will give me my 6 hydrogens. And now I'm going to work out what number I need to times my oxygen by to balance out with the oxygens on this side. So I will maybe show you my counting here. So I've got 2 times 2, 4 oxygens on this side, plus another 3 times 1, which is 3. So that'll give me 7 oxygens on this side. So in order to have 7 oxygens on this side, I'm going to need, well, I've got 1 oxygen here, so I just need to times this oxygen by 3, and that's going to give me 1 plus 3 times 2, which is 6, so 1 plus 6, which is 7 oxygens on the left-hand side. Okay, so that was just a little bit of practice of balancing equations. You probably won't be asked a lot about combustion in the context of this topic, but it should be general background knowledge that combustion is an oxidation reaction. Okay, and combustion we would say is complete oxidation of the hydrocarbon. Okay, so like I mentioned, combustion is an example of complete oxidation. What we're going to look at mostly in this topic is what we call mild oxidation. So I've moved on to page 22 now, and let's look at the top of that page. So we're going to really be focusing in this topic on mild oxidation. So if we read this sentence about mild oxidation of alcohols, it says the complete combustion of alcohols breaks all the bonds in the alcohol. Okay, so I talked about that a little bit already. Milder oxidation of alcohols can occur affecting only the functional group and leaving the carbon chain intact. To undergo partial oxidation, I should have a comma here, alcohols require an oxidizing agent. This can be thought of as a source of oxygen. Hot copper oxide and acidified potassium dichromate are suitable oxidizing agents for the mild oxidation of alcohols. So when we're using an oxidizing agent, remember the oxidizing agent is an electron acceptor, and therefore itself is reduced. So if there is a reaction, if oxidation of the alcohol occurs, then there's going to be probably a colour change. We tend to use oxidizing agents that change colour, so there will be a colour change. And it's the oxidizing agent that will change colour. Okay, so you're going to look at some separate videos in a little minute, and I'll show you one for hot copper oxide and one for acidified potassium dichromate. So the two oxidizing agents that we're going to look at are hot copper oxide and acidified potassium dichromate. In the video, you need to pay close attention to the colour change if a redox reaction occurs, because these colour changes come up quite frequently in exams. But you should be able to get that information from the video, and actually it's on this page lower down. So for hot copper oxide, I'm just going to show you a video with a generic reaction between hot copper oxide and an alcohol. And then I'm also going to show you a video which compares the oxidation reactions of 3 different types of alcohol, which you need to class as primary, secondary or tertiary, and then you're going to record the observations on reaction with acidified potassium dichromate. Okay, so I want you to pause the video now, and I want you to see if you can classify these 3 alcohols as primary, secondary or tertiary. Okay, I hope it wasn't too obvious, but they actually go in that order, so primary, secondary and tertiary. I've just sketched the full structural formula of these. So butan 1-ol primary, because the carbon attached to the hydroxyl group is only bonded to one other carbon. Butan 2-ol secondary, because the carbon that's bonded to the hydroxyl group is bonded to two other carbons. And 2-methylpropan 2-ol tertiary, because the carbon that's bonded to the hydroxyl group is bonded to 1, 2, 3 other carbons. So what I'd like you to do is pause this video. I'm not going to go through the answers to the rest of this page because it should be really obvious from the videos. So when I come back to the next section, I'm going to be looking at page 23. So like I say, you can finish this video now and look at the description of the video, because I'll put links to the other videos that I want you to watch, which shows different reactions of oxidizing agents, hot copper oxide and acidified potassium dichromate with alcohols.